let's get started. Thanks for joining this talk on active treatment systems. My name is Nick Buckner, and I'll be presenting on behalf of Clearwater Services. I've been involved in the water treatment industry for about 8 years, and now I focus mainly on project management and estimating. So I was trying to get our marketing team to create a short TikTok video about water treatment, but we couldn't find anyone brave enough to step up and be the main character. So this will have to do. The short presentation focuses on the basics of water treatment. If you have any questions or comments, you can either drop them in the chat or just type up and ask them. Let me just start out by saying that I understand that active treatment is somewhat of a daunting BMP when comparing the costs and logistics to installing silt fences and straw wattles, right? It is my intention through this presentation to give you as much background as possible so you will understand some of the components when it comes to active treatment. So a little bit about Clearwater Services. We are a water treatment company based in the Pacific Northwest. We have branches in California and a branch in Michigan. They're mainly focused on building the filtration vessels, some of which you'll see in the presentation. We have many industrial and construction water treatment projects all over the country and expanding our market footprint all the time. By taking the time to truly understand all the project variables, as well as our clients' needs, we strive to be the best turnkey solutions provider for water treatment systems and needs. Okay, that's enough of the advertisement slide. On to the good stuff. Active treatment systems. So why and when is treatment utilized in stormwater management, active treatment? Basically, your standard BMPs aren't suitable to reach the regulatory requirements for a discharge. Let's say, for example, you have a project with all the BMPs imaginable installed, but the project is not shutting down for the wet season. Rather than making the construction workers pull up giant sheets of plastic or tear up that freshly laid hydro seed, every time they want to get something put in the ground or moved around, we can utilize an active treatment system. Or let's say the project was red tagged by the city or the DOE for excessive water quality violations. These fines and delays in work can get extremely expensive really fast and will quickly outpace the cost of having a treatment system in place. Or it might be required to have a treatment system during dewatering, especially if there is potential existing contaminants in the soil or water and the project has an administrative order. It is almost always better economically if the treatment system is incorporated in early design and planning of the project rather than a last-minute emergency. So what does 25 NTUs actually look like? Here are some photos to give you reference. Remember that turbidity is cloudiness or haziness of a fluid caused by large numbers of the individual particles that are generally invisible to the naked eye. It's kind of like smoke in the air. 20 to 25 NTUs is actually pretty clean and mostly clear. It's quite hard to meet this benchmark without active treatment if you are working a construction project. So if they're actively working on the site, tearing up, moving piles of dirt, disturbing soil and stuff like that. Especially if you have clay like soil and lots of exposed soil with like very minimal retention. So it's hard to rely on gravity settling and just retention alone to meet the discharge requirements. That's where active treatment becomes the next best management practice. Any questions so far? Anybody? Comments? Nope. Yeah. So Here's a little treatment technology matrix generated in-house that shows simple to complex treatment technologies. Basically, as the site-specific factors increase on the x-axis, flow rate, pollutants, and dissolved contaminants, so does the initial cost and level of treatment complexity. The risk and need for higher performance is increased as well to meet the regulatory discharge demand. So talking a little bit more about active treatment systems, some of the components, and how we design them for specific projects, understanding the size of the site, the start date and the duration of the project, as well as considering if there's any available on-site storage that we can utilize. We can then start working on figuring out a suitable system flow rate and a recommended storage capacity. So if we don't have, the site doesn't have big enough ponds, we can kind of recommend additional tanks or increasing the flow rate that the CESF system can hit. So a pre-settling basin or a temp pond provides pre-treatment of the runoff in order to remove large suspended solids. Usually runoff treated by pre-settling basin, it's not discharged directly to a receiving water unless it has a very long time to settle. You'll probably get it, a lot of times it'll drop out to like the 280, 300 ATU if it's big enough, but you're still above the 250, which is, you know, you have to report to ERTS if you're going to discharge it. I myself love it when I see a project will have a pond installed that we can use for storage. It's like the cost savings of not having extra tank rental, sludge management, because a lot of the heavies will fall out in the pond, and the treatment tech hours for the time that we have to go out to the site to process the water. It outweighs the price to create, you know, a pond of at least some size. So I'm always asking my clients for bigger ponds, but you know, for some sites, it's just not an option. So a lot of the city sites or really small projects, we're gonna have to rely on tanks, right, for storage. So first off, you need to know that if you have a active treatment system, you will need at least some storage capacity and likely at least some treatment tanks. These tanks shown here are poly tanks and steel frac tanks. So the sediment ponds are also used for stormwater retention and sometimes water treatment. Ideally, if the settable solids should be removed through more conventional BMPs, and an active treatment system should focus on total suspended solids. But on active sites during the wet season, we see water that should just be called what it actually is. It's mud getting conveyed to the treatment tanks. And they say they don't have time for the mud to settle, you know, they got work to do. So you guys deal with this. Normally, an active treatment system will utilize initial storage for the upfront solid separation. So that's, you know, the silt pond or a weir tank. You'll get the real heavies falling out in those structures before they go into the treatment tanks. Once we get some of the heavy solids dropped out in the pre-treatment tanks, then we push it, you know, to the treatment tank, and then it's going to go through a sand filter for final polishing. So sand filtration. Talk a little bit about those units. So traditional construction stormwater BMPs are used to control soil erosion and sediment loss from the project, but they may not be adequate to remove enough turbidity to be under the allowable benchmarks. Pressurized filtration can be used to remove the last bit of sediment that's not falling out by gravity and get that site silt-laden water looking like rain. Sand filters differentiate by pod diameter, size, sidewall size, and number of pods. Back in the late 1900s, over 20 years ago, it was discovered that adding some flocculant to dirty water, chitosan, and running it through a sand filter might be the best thing for active construction projects to keep them rolling along through the winter. And we all know how long the winters are up here in the Northwest. It just doesn't stop raining, so. I've heard many stories about projects. They would just stabilize the whole site and shut it down as soon as October hit. And then, wait until the sun came back for them to keep working. This was before, treatment systems were available. So the cost of the economy with all those construction workers out of a job during the winter, it must have been huge. Like, it'd be interesting to see a number on that if anyone could estimate it, but I can only imagine it's big. So let's go over some technical aspects of sand filters. Pressurized sand filters, they're designed for water filtration down to 20 microns. They're a durable metal filter that usually come equipped with a simple backwash system for consistent operation. These units have to be rugged and well maintained to sustain the amount of water that gets pushed through them. We typically use silica sand for our media in these units, but crushed glass and green sand, along with some other specialty medias, are used. I just want to mention bag filters versus sand filters. A lot of guys want to get bag filters because they think they're going to save money, but typically they won't be able to remove the sediment below 30 to 50 NTU. Even if it's a lot of concrete washout and fines like that, it won't, you're just fighting that uphill battle with the bag filter. And then you have to add in the cost and the hassle of changing out the bags. I just think the sand filter is a better option for a long-term project. So using some chemistry, some tanks, and a sand filter, we can take water that is well over 2,000 NTU. Like, it won't even show up on our meter. It's so dirty. Run it through the process and we can get it down below 1 NTU, like almost within drinking water, standards. Of course, with drinking water, you need reverse osmosis for the final polish. So sand filters come equipped with these backflush functionality. It's a self-cleaning process. It self-cleans the sand, and it's triggered by one of two things, right? Either it's on a time frequency from the controller, or it's on a pressure differential set between the inlet and the outlet manifolds. So if the pressure on the top bed is raising higher than the low pressure, you know that you're getting impacted on media, and you need to get that dirt blown off the sand, clean up the sand. So when this happens, there's either water or air pressure. It opens a three-way valve, causing a reverse flow of one of the filter pods. So the water gets pushed up back through the bottom of the sand bed. And it hydraulically, it liquefies the sand and pushes most of the dirt goes out. So you set the pressure so you're not pushing all the sand out, because the dirt's going to be lighter than the sand, right? Then it'll run through the cycle. It'll clean one pod at a time while you're still pushing water. If the water's, relatively clean, it can still discharge. Sometimes it'll spike and have to go into recirc for a little while you're doing the backflush cycle. So, advanced treatment system. Let's talk a little bit more about it. They're very similar to active BMPs. However, we're adding some chemical and potentially adsorption material for harder contaminants or dissolved metals. It's probably the most complicated BMP. Some of the advanced options on the market are chemically enhanced sand filtration, CESF. It's done with chemicals including but not only chitosan. We use a variety of flocculants for this process. There's also electrocoagulation, which uses electricity to clump up the particles so that they're easier to filter out and drop out. And then there's adsorption and ion exchange resins. So chitosan is not always the preferred chemistry. However, it is the most common. Chitosan, or chemically enhanced sand filtration, is the most used treatment technology in the Northwest. And it's the most used by us at Clearwater. Ideally, CESF is looking to be utilized on sites that have high volumes of stormwater runoff, and they have a tough time with settling out the existing solids or soils at high volumes. So it must be incorporated to remove the contaminants of concern. I mean, sometimes we use a CESF system before we use a specialty media because it'll remove a lot of contaminants as well. Some of your hydrocarbons and even some metals to be a little cheaper alternative than going straight to carbon. So why the fines don't settle out naturally? Ideally, we use the chemicals to have adequate sediment reduction. This is often necessary to provide the water suitable to the surface surface waters of the municipal, sewer system or even like surface waters, right? So if we don't use the chemistry, we're not going to be able to hit that 25 NTU benchmark to discharge it to the stream. A lot of times it can be a little bit higher for the sanitary system. They're just worried about the really heavy stuff. So we'll add a flocculant or coagulation material to often, we'll add it when the turbidity just won't drop out, when it just won't drop out even naturally or pushing it through the sand filter. They're just so fine that we need to add another little bit of treatment to get it to fall out better. It's due to them being like the particles are so small, you just can't catch it with the sand. So that's when the flocculants come in. So we've heard about flocculation and coagulation, but what is it? Flocculation is a physical process in which the fine particles come out of suspension in the form of flock or flake due to the addition of a clarifying agent or a polymer. We're basically bringing the destabilized particles together and making them bigger so they can drop out of the water or be filtered more efficiently. Coagulation is a chemical process usually utilizing a metal salt in which the salt breaks down to release the charge and neutralize negatively charged colloids. Like with EC, one of the downsides of EC is it doesn't always get the superfine turbidity particles clumped together enough to be removed by filtration. So it'll knock it down really low, but it's not quite low enough when you use EC. A lot of times you'll have to hit it with a polymer at the end for the polishing, the polishing factor of it. So a basic CESF system treatment process, a typical active treatment system, it'll follow something like this diagram shown. We start out with preliminary storage, maybe a sediment pond, a lift station, a sump, or even just a standard frac tank. Like they'll convey the water to a tank and we'll start the treatment process. The water is pulled out of that through a control unit. It's monitored for the turbidity and pH, checks the flow, and then we'll usually add some pre-treatment chemistry. Water then travels into an additional location So either another tank or a cell in the pond for some more gravity settling, now that it has some of the chemistry in there. Then after the pretreatment and settling, it's pushed through the control unit again to check the turbidity and pH and collect some data on that. Then it goes through the sand filtration. After the sand filter, it goes back to the control unit for final monitoring. So if the water is within acceptable range, it can be discharged at that point. It gets logged, and if it's not within the range, it gets recirculated and sent back to the original, the original location or back to another tank so that it can be processed again. Let's call it recirc. So here's a video of chitosan lactate being added to sediment-laden water. You can see it's made out of crab shells. So you can see that there is some vigorous mixing. It's to get the reaction going. Suspended sediment particles start to bind to the polymer and create larger, denser particles, which now fall to the bottom of the beaker. In the chitosan CESF system, we'll pull the water off the top of this. We'll keep, all these solids down in here, and then we'll push this through a sand filter to remove any of the fine particles and residual. This is a quick video of one of our treatment systems in the field. This is a permanent installation, one of our industrial projects, but it's very similar to our construction systems. Kind of cool drone shot here. Going up into one of our control units now. So you have the chemistry storage there on the left, and then turbidity and pH monitoring devices. Okay, any questions? Anybody? Okay, so residual chemistry testing. So let's talk about this a little bit here. So water, if we're using chemistry, we want to make sure we don't have anything residual in the water after we filter it through the sand filter. That's where these tests come into play. It's a requirement of the GULD, General Use Level Designation, when you use CSF, that these have to be performed. And it's just good practice, even if they weren't, required. Make sure that we're not doing more harm than good. So the current testing kits on the market, so chitosan is considered non-toxic to animals, but when it's dissolved in acetate, it's in liquid form. There has been acute toxicity found for rainbow trout at around 22 parts per million. That number assumes a high concentration of chitosan residual in clean effluent. In order to confirm that we are not hitting anywhere around that concentration, we look to do residual chitosan testing. This test compares a field water sample and a spiked solution of chitosan. If there is greater than 0.1 part per million of free residual chitosan, then a brownish purple color will develop on the test filter. If the color from the discharge water is as dark as the spike test, then the test is a fail and the treated water has more than 1.1 parts per million of chitosan residual. So the water can't be discharged and it has to be recirculated until it passes the residual test. These tests are required to be performed at least 2 times during an operational period. So when you start up and then a couple hours later. The good news is that sand filtration is very effective at removing chitosan from water. So the likelihood that residual chitosan will be found in a properly designed and maintained sand filter system it's extremely low, very unlikely. So pH adjustments, we have to be able to be hitting that range of 6.5 to 8.5 to discharge to the surface. And also we want to adjust the pH for our treatment chemistry to work better. A lot of times it just won't work at all if the pH is out of whack. So one of the main causes for high pH on a construction site is a cement pour, or they're crushing up concrete or something, along those lines. We typically use a food grade citric acid to lower the pH and sodium bicarbonate to raise it. And also, it adds some conductivity for the chemistry to work better. If we have really intense pH levels, we have to use like more aggressive chemistries to neutralize the water. So we like to use the food grade stuff because it's just easier and safer for everyone involved. I don't know if that chat box is showing up to you guys too, right in the middle of the screen. So if further contamination reduction is needed after the CESF process, normally we'll incorporate the adsorption equipment on the back end of it. This usually comes in these tall vessels like shown here. It's a 5K vessel on the right. Those are probably 2Ks on the left. Normally we design the adsorption to have roughly 10 minutes of empty bed contact time. So that basically what that means is every drop of water will hit this media for 10 minutes. So we'll adjust the flow rates and figure out exactly how much media we need to bring out. We also try to have a duplex system so that we can establish lead lag vessels. This works better for media change outs because you only have to change out one vessel at a time, and you can switch the orientation of the vessels, to compensate for the overall loading. So here's a few common medias that we use for adsorption. Granulated activated carbon, or GAC as we call it. It's usually derived from coconut shell. The best for removing hydrocarbons, but it also can remove some metals and VOCs. Then we have the react carbon. Basically think of that as recycling carbon that's already been used. This is it's a process of heating the carbon to like a really extreme temperature, and it releases some of the contaminants that were attached to it previously. It's good for projects with less liability and a lower discharge benchmarks, like if you're going to a sanitary sewer system. And then we have like medias like zeolite. It's an aluminum silicate, and it consists of silicone, aluminum, and oxygen ions. It's good for like your VOCs. There's more options like biochar, compost, emitted sand, etc. that work as well, but these are the most common types we use, and you'll probably see out there. So now that we've covered sand media, adsorption media, and chemistries, let's talk about the control units. Inside a control unit, you might see chemical metering pumps, valves, probes, and a computer of some sort, a PLC or a Vulcan or Hawk mainstem. We like PLCs because we have more ability to control them and automate. So the system controller It controls the flow of water from the A to B in the treatment process by communicating with the pumps and valves. It'll also likely record and collect data and control chemistry injection. Inside the control unit, there may also be like a lab bench for water quality testing, bench scale treatability, logs, and chemical storage. So a few things to consider for chemical injection or introduction. Is it being hand mixed and added to the tank, or is it a chemical that's already mixed in liquid form and just needs to be injected into the water somehow? It's common for chemistry to be delivered by a liquid metering injection, the LMI. That's what's on the left here, LMI pumps. So the pump can regulate the speed and the amount of chemistry that's getting dosed into the water. There can be multiple points of injection for different chemistries. You might have a pre-treatment chemistry for initial flock with pH adjustment, and then later down the line, you'll have a polishing chemistry. The polisher is used to grab that last bit of fine particles just prior to the sand filtration, so that it's more efficient. So let's talk about remote control technology, automation, in the world of remote living that we're all in now. Remotely available control system that'll save tons of money on operations. System can be viewed on a tablet, a smartphone, or a PC. Basically emulates what is visible on the computer inside the control unit on the PLC screen. This screen here is from one of our industrial systems. It's kind of like showing you the pumps, the flow rates, total water volumes, and you can click through this basically to get access to more controls and data. And then this is another photo of it that shows tank levels. We can set high level alarms. You can tell the pump when to come on and when to shut off in the tank, so it it doesn't overflow the tank, and then it doesn't suck all the bottom silt off the bottom of the tank. So I mean, obviously these screens are showing you like fully automated systems. Some systems are manual, and you're just manually turning a pump on and off, switching the valves around. You got to be on site, every time that water is getting processed. So as a quick summary, here are my initial thoughts. If you think you're going to need, active treatment of any kind, so know your site, understand construction phasing, the soils, the existing contamination, and if the project is continuing through the wet season. Have early design talks for a treatment system to go over the footprint, flow rate requirements, power requirements, and what benchmarks you want to hit. Understand what technology you're getting, what are the expectations. Always ask questions, to understand what you're getting, so that it'll make more sense, and it'll just be easier for you when we're up and running and we're running into any problems on the site. You'll just be in the know better. It's a good idea to know about like consumables. If you're going to need chemistry, if you're anticipating a big concrete pour, you're going to have pH adjustment chemistry. If you're tearing up, half the site, it's going to be really dirty, so you're going to have more chitosan or P50 costs. And like, always got to tell the clients, contractors, everyone working on the site, active treatment system is just one BMP. It'll always work better when there's other BMPs installed. So don't just assume I have a treatment system on site, I don't have to do anything else to the site, right? It's going to save cost and headache if you stabilize the site in some sort with other BMPs. So That's all I got. Hopefully, if anyone has any questions, you'll ask them, or you can email me. My contact card if you want to take a picture with your phone. Takes you to the web link to get my contact card. So yeah, any questions?
Go ahead and unmute if you have a question
or comments. What are you guys eating for lunch?
So thank you, Nick. I'll make a comment here. In my 22 years at the Port of Seattle, we treated something around 750 million gallons of construction stormwater using this type of system, the chitosan-enhanced sand filtration. Very effective system. SeaTac Airport has very strict discharge requirements to the creek. I think it's 5 NTUs daily average or something. And this is the only way that the port could achieve that number. So I highly recommend, especially if you are definitely going to be working over winter, plan it into your project early. It'll save you a lot of hassle, a lot of sleepless nights. So that's my little advertisement.
Awesome. Thank you.
Hey, Dave. Christine. There's also consideration. I know we worked on those port projects together. If you're doing early design, to understand what other products the construction or the contractor is using that might have potential conflicts with different chemicals, different flocculants, different chemistries. Because I know we experienced that ourselves at Port of Seattle, just a general organic influence. And I know that happens on other construction sites, but if there is a possibility to do early design to actually get an understanding of the full construction scope, not just the water treatment scope.
Thank you for that. Yes, if you hydroseed and continue to treat water after you've hydroseeded before the grass grows, you could have problems. I think that was one of our biggest problems, wasn't it, Christine? Was the bonded fiber matrix.
Yep, and the concentration of the product and timing when it relates to storm events, and getting kind of a lot of the flush of material and product into the treatment system. So just those little influences, they're variable, but they happen, and it just affects the design and selection of chemicals that we're using out there.
Great, excellent. Some jurisdictions require, if you want to work through winter, that you use a system like this. Is that still true? I remember City of Redmond. I think there's some other ones.
Yeah, I know City of Redmond wants you to have a plan in place to deal with the stormwater, and like the storage requirements are excessive in the City of Redmond, but you subtract what the system can process, so you don't have to have 1 million gallons of storage on a 1 acre site.
And I don't know if you can answer this or directly or give kind of a ballpark. But what could somebody expect to pay per month for a system like this? Is that something you're comfortable saying? I mean, I can throw out a number that we used for planning.
Yeah, I mean, it's totally variable on the size of the project and the contaminants and stuff like that. So I hesitate to throw out a number, and then it's best I could put together a number if you gave me a project, put together a rough number within probably 2 hours.
Sure.
I'll chime in here for Nick on that. Again, it definitely depends on the size of the site and other specific conditions. Short duration projects are obviously going to have a much higher monthly cost because there's a lot of installation and removal cost. But you could pencil in, including installation and removal, somewhere between $30,000 and $40,000 a month for most projects.
Yeah, thanks, Duncan. That's actually, I think we figure 35 to 40 just based on experience at the port. So just for planning, it can be more, it can be less, but just so we get a number and a contract that we're going to put out to bid. Any other questions or comments? Okay, this has been great. Thank you, Nick, so much for presenting it. This is really good information. If you folks haven't seen the chat, please go to our website, chapter website, PNW-IECA.org, for links to our YouTube channel where this will be posted, and a lot of other cool stuff. So with
I'll
that,
keep working on that TikTok video too.
okay. All right. Thank you all for attending, and hope to have you attend next month.
Thank you.
All right. Bye, everybody.